Welcome to the notes for 1-3. In this lesson, we're going to do a quick review of transformations of parent graphs. This is something that you should have covered in Algebra 2, but it may have been a while, so we're going to practice it and make sure that we feel good about it as we move deeper into pre-calculus. Let's get started. So the first transformation we're going to look at is when we have a function and we're going to, it could be any function that we're looking at there, but what happens when we add something to it? Okay, and last year in Algebra 2 we talked about it was k, the k value. So this is going to cause a vertical shift, right? So we're going to do a vertical shift. It means we're going to move our graph up and down however many units we have for k. So let's look at our first function here, y equals the absolute value of x. This is our parent graph for absolute value. So if you think back to your absolute value parent table there, we would have had -2, -1, 0, 1, and 2. The outputs for this one were 2, 1, 0, 1, and 2. And it made that nice V shape, right? It made that nice V shape. Sorry, I'm trying to draw as accurate as I can without a ruler. So now, when we look at what happens when we take that absolute value of x, y equals absolute value of x, right? And now we take it and we add 5 to it, right? That's like our k value. So what ends up happening, remember, is we're going to take all those y values and we're going to increase them by 5. That means that all the outputs in our function would increase by 5, which essentially is going to shift our graph up 5 units. So it looks like we'd have a point at -2, 7 instead of -2, 2, right? So we go up 5 units up to -2, 7. We'd have a point at, instead of -1, 1, it's going to be -1, comma, 1 plus 5 would be 6. We'd have a point at 0, 5. We'd have a point at 1, 6, and 2, 7, and then so on. We can see the shape now, so we can connect them and draw it out. But we can see that this graph went up 5 units. You know, same thing at the end here, right? When we are subtracting 2 from that function, that means our outputs are all going to end up decreasing by 2. Right? So when you think about that, all of our outputs actually end up decreasing by 2. So we would end up with a point at -2, 0. We'd have a point at -1, -1. We'd have a point at 0, -2. And you can see when you compare it to our original graph over here, right? Everything has been shifted down 2 units. So go ahead here and just kind of throw some points on here and then finish connecting it. Just like that. Okay, so that is the effect of that k value. It's a vertical shift. Underneath it says what equation will result in the parabola y equals x squared being shifted down 4 units. Right, so we're going to go with, right, when we shift it down 4 units, that means our k is going to be like a -4. So we'll go from y is equal to x squared to y is equal to x squared minus 4. If we were looking at building our tables, right, and we don't have to put any values in it here, we would have started out with our parent table, and then our transformation table would have been, still the x's would have been the same, right, because we're just shifting it up and down, and then all of our y values would have decreased by 4. Let's move on, try another one. So the second type of transformation you learned in Algebra 2 would have been the horizontal shift. Okay, remember the horizontal shift is when we're going to affect x's, right? Our x coordinates are going to change. So when we look at that, we're thinking about if we had any function, it'd be like y equals f of x minus h, right? Wherever x is, that h is going to be with it. So that's what affects our horizontal points. So we're going to use this here to move some graphs left and right. So this is a horizontal shift. Let's use our cubic function just to help us as an example, right? So we'll put our parent table here. We have x and y. We have -2, -1, 0, 1, and 2. And so remember, every time we plug in a number here, right, it's like we're taking it and we are cubing it. So when I plug in -2 and cube it, I would end up with a -8. -1 cubed is -1. We'd have a 0, a +1, and a +8. And we'll plot those on our coordinate plane. So -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. Connect those, make our cubic function. So the thing that we have to kind of remember is when we took x and we added 2 to it, what was the transformation that happened? Okay, so when we have this x minus h up here, right, when we have +2, we have to remember that it kind of affects the graph the opposite way from what we would think, because we're going to have to be moving our parent graph back to its original location. So what value of x could I add 2 to it there to get it back to like where it was? And without having that table up here on here, that kind of probably doesn't make much sense. So let's take a look and see here. Right, if I took this, I'm going to kind of do it over on the side down here. Right. Remember, when we see +2 in here, this is a horizontal shift to the left. So we are shifting our graph to the left 2 units. Well, anytime you move something to the left 2 units, right, you're thinking about you're going to be subtracting. So we need to subtract 2 from our x coordinates. So we're going to say x minus 2. That's what's going to move our graph to the left 2. We're not doing anything to our y's, so those will actually end up staying the same. I'll just go ahead and write those down. -8, -1, 0, 1, and 8. And in this case, we're just going to be taking the values that we have up here, -2, and we're going to subtract 2 from it, and that's going to give us -4. We'll take our -1, we'll subtract 2 from it, and that will give us -3. And then 0 minus 2 would be -2. We'd have 1 minus 2 would be -1, and then 2 minus 2 would be 0. So you'll see our points are at -4, -8, -3, -1, -2, 0, -1, 1, and 0, 8. And you can see when we reconnect our points or rebuild our function, it has been shifted to the left 2 units. Okay, now we can look at the last one, right? If we have y equals x minus 6 to the 3rd power, right? So let's think about that for a second here. Which way is that going to shift it? This one should shift our function to the right 6 units. Okay, so you gotta kind of remember it's always kind of the opposite of what you see when we're talking about horizontals. All right, so our rules for our graphs kind of change and kind of become the inverses. So our y is still not going to change, but now we would have to add 6 to each of our original points. So we started out, remember, with -2, -1, 0, 1, and 2, right? So when I take those and I add 6 to them, I get 4, I get 5, I get 6, and then if you could just continue the pattern down, it'd be 7 and 8. And then all of our x coordinates will actually remain the same. We had -8, -1, 0, 1, and 8. And let's go ahead and plot those points on here. So at 4, -8 would be down here. 5, -1, 6, 0, 7, 1, and 8, 8. And we will just rebuild that function just like that. Okay, so I know some of us didn't use the tables last year, but you're going to want to use the tables this year. So that's why I want to make sure I'm taking the time to show you how to do it, because it's going to help us, especially when we get to some of the arbitrary graphs and functions that you're not so familiar with. So it says, what function would you use to shift y equals the square root of x 2 units to the right? So on 2 units to the right, so remember we're going to say y is equal to, and if we're going 2 units to the right, that's like our h, right? We're going to say x minus 2. So in our equation, that's what it's going to look like. If you're talking about like what would be the effects on the table, right? If we had y is equal to the square root of x, you would have had your original x comma y, but that would have shifted then to become x plus 2 comma y, right? Because that's going to shift it right to when you add 2 to the x coordinates. All right, so next one. Given the function f of x equals 1 over x minus 4, and then we're going to subtract 3. So what is the parent function? Well, this one is a hyperbola, right? This is a rational function. Right? We call that a hyperbola. Okay? And we know the equation for that would be just y equals 1 over x, where our h and k values, right, would be 0, 0. And the special thing here, right, about this locator point at 0, 0, remember this is called the locator point. For a rational function here, our locator point is where the two asymptotes cross. So what we're looking at here, I'll say where they intersect. That's more of a math word, right? Okay, so our parent function, remember, if we were to think about our x-axis and our y-axis, right, there's our x-axis, there's our y-axis, we would have a vertical asymptote that runs down here, a horizontal asymptote that runs through here, and then what we end up with here, right, is if we go over one, up one, and back one, down one, we would actually have our hyperbola that runs like this. Remember, it runs right along those asymptotes, but it never actually crosses, so looks like this. So when we're talking about the function up here, f of x is equal to 1 over x minus 4 and then minus 3, it says describe the transformations. Well, when we look at this piece of it here, right, that means it's going to be shifted to the right 4 units, and it's going to be shifted down 3 units. Okay, so anything about your table would have gone from x comma y to, right, if we're trying to go to the right 4, we're adding 4 to the x coordinates, and if we're going down 3, we're subtracting 3 from the y's. Okay, and you can use your parent table if you want, or this is one of the ones here where I think sometimes it's easier just to move the function, right? We know originally this is where the asymptotes would cross at the origin, but if I shift that over to the right 4 units and then down 3, I end up at a new point, which is 4, -3, right? This would be our new locator point is going to be point 4, -3. And that's where our asymptotes are going to cross. So let's just redraw in the asymptotes. zeros in here. Now because there is no stretch factor, we're still just going to go from our locator point over 1, up 1, and back 1, down 1. Okay, and then we will connect those. We'll run our asymptote down here, hit it, connect that with this side, and then we'll run our asymptote along the asymptote, here. We'll actually hit that point and then go down. Remember, we don't want to cross those asymptotes. So we have actually shifted that. Now it says, does the order in which we perform the translations matter? On this one, since we only have one horizontal and one vertical transformation happening there, no, it should not really matter here, right? And you could even look at it here. If I move it over 1, 2, 3, 4, and then down 1, 2, 3, I end up in the same spot. Or if I went down first, 1, 2, 3, and then went over 1, 2, 3, 4, I still end up in the same spot for that locator point. So in this case, we would say no, it really doesn't matter on this one. Is that no for all of them? Absolutely not. There's actually some that will matter, but it just depends on the amount of transformations that we have happening. All right, so we got another one here. Y equals the square root of x. Right, this is that shooting star shape, and you see I already kind of have a table started. Remember, our domain for this one, we want to use perfect square numbers. So when I take it and I plug in 0, the square root of 0 is 0. Square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. They don't all fit on there, but we'll just plot them on there the best we can. 0, 0, 1, 1. 4, 2, and then we have 9, 3, which would kind of be off there. It'd be kind of somewhere over here. We'll just draw that part in. Okay, so what we're going to be looking at here, right, we're starting out with y equals square root of x, and then we're going to take that y equals the square root of x, and we're going to multiply it by 3 in one of them, and we're going to multiply it by -2 in the other. So what we're looking at in this one is y is equal to a times our function. When we multiply a number times our function, remember this causes a vertical stretch or compression to happen. Okay, or compression. I'm going to run out of room there, so I'm just going to abbreviate compression as COMP. Okay, so when you think about a vertical stretch, does that affect your x's or your y's? Right, and you think about y's run vertically, so that's what we're looking for here. So when we look to build our table, right, so we can kind of compare it to our y equals the square root of x table, our x's are not going to change. They're going to remain 0, 1, 4, and 9. But our y values will change because we're going to multiply that output by 3. So we're going to say 3 times our y value. So we're taking these values over here and multiplying them each by 3. Right, because that's going to give us, so we multiply, we'd have like 3 times the square root of x. Okay, so when I do 0 times 3, I'm going to get 0. 1 times 3 is 3, 2 times 3 is 6, and 3 times 3 is 9. Let's go ahead and plot these on here. Let's see. All right, so our original point is still on the origin because you can't really stretch it off the origin. Instead of going over 1 and up 1, we're going to go over 1 and up 3, so we're at the point 1, 3. We're at the point 4, 6. And we'd be at the point 9, 9, which would be like way up here somewhere. Doesn't have to be super accurate because it's off the graph, but this is what we're looking at. Okay, now when we look at this last one here, remember, when we have a negative in there, when our a value is negative, usually this causes a vertical flip, right? So instead of going up, this one's actually going to go downward. So let's actually see how that happens with our table. So when I build my table, again, nothing's happening to our x's, so we're still going to have 0, 1, 4, and 9. But now we're going to multiply our y values times -2. And again, we are referring to these y values over here. So 0 times negative 2 is 0. We have negative 2 times 1 is going to be negative 2. We've got negative 2 times 2 is negative 4. And then negative 2 times 3 would be negative 6. Let's plot those points so that we can see. We've got 0, 0, 1, negative 2, 4, negative 4, and then 9, negative 6 would be somewhere down here. But we can see now how it's made our shooting star go downward instead, right? Shooting out that way. But it also still has a little bit of a stretch. All right, so how can we write the general rules for these transformations? Remember, for our vertical translation, it was y is equal to, and it doesn't matter what the function is, whatever the function is, we are going to take it and we are going to add a k value. That's going to shift it up and down, left and right. For our horizontal translations, whatever our function is, we are going to have that h value is going to be subtracted inside whatever the grouping symbols are. That's going to be our shift left and right. And then our vertical stretch compression, right, whatever our function is, we are going to be taking it and multiplying it times, in this case we'll say a, right, because that's like our stretch factor. And we'll experience some that have more than one of these in there at the same time. All right, so last little bit says suppose that we have a stretch and a shift. Doesn't matter in which order we perform the transformations. Truly, the answer is sometimes. It can be yes, it can be no. If you have more than one vertical or horizontal transformation, when we set up our tables, okay, we want to make sure that we perform our transformations using like the order of operations. So as we look at this one here, like saying like what's happening, remember this is the same thing as y is equal to negative 2 times the absolute value of x plus 3. Okay, don't get hung up on the fact that that 3 and the negative 2 are both out there. Okay, so when we look at this one here, this one's got 3 transformations. There is a vertical flip because of the negative on the 2. There is a vertical stretch. And there is a vertical translation or vertical shift up, right? So since we have multiple vertical things happening here, we want to make sure we're careful when we're building our tables. So let's just go ahead here and build our original table. We're going to do it on the left side. So we have negative 2, negative 1, 0, 1, and 2. I know it's really small down there. Sorry, I'm right at the edge of the paper. But when we take the absolute value, we'd have 2, 1, 0, 1, and 2. So I'm going to go ahead and plot that on here. This is our original parent graph. So we've got this one coming down here, going up this direction. Remember, this is just our parent graph. Y is equal to absolute value of x. So when we build our transformed table, okay, nothing is happening to x here, right? Because we had no horizontal transformations with that x. So we're going to go ahead and leave our x values as negative 2, negative 1, 0, 1, and 2. But when we deal with our y's, right, we want to make sure we perform this in using the order of operations. So since we're going to be multiplying times negative 2 and adding 3, we want to use the multiplication first. So we're going to write our rule as negative 2y, then plus 3. So we're going to apply our stretch first, and then we're going to shift it vertically. So all we're going to do is we're going to take these values that we have on our original table, and then we are going to multiply them times negative 2 and then add 3. So if I said negative 2 times 2 plus 3, that would give me, what is that, -1. If I did -2, I'm sorry, that should have been, yeah, -2 times 1 plus 3. Remember, these are coming from over here, what I'm inserting for x. I would get -2 times 1, that'd be a +1. When I plug in 0, I'm going to get 3. Then we're going to plug in +1, right? And that should be the same thing we got above, so that should be a 1. And then the last one, -2 times 2 plus 3, and that should take us back to -1. So let's plot those points, right? We've got a point at -2, -1, -1, 1, 0, 3, 1, 1, and 2, -1. And that should help us to kind of see our shape. So here we go. -2, -1, -1, +1, 0, 3, 1, 1, and then 2, -1. And you can kind of see the slopes of the sides, so we could continue to go down 2 and over 1, down 2 and over 1 to extend them. And we will connect those sides, and you can see we now have a graph that we took our original one here and we vertically flipped it so it opens down. You can see that the stretch, right, instead of going over 1, up 1, it now goes over 1, down 2. There's the stretch. And the fact that we moved it from 0 all the way up to 3, there's our vertical shift. So hopefully that helps you to understand or review over some of these concepts. If you have questions, please ask in class or visit Math Help. Okay, it's important that you ask now before we get deeper into it. Thanks for watching.